Okay, good day everyone. My name is McDonald Chirara. Thank you all for joining us today for this lecture. Today we have a special speaker, Dr. Martin. So Dr. Martin grew up in St. Louis, Missouri, and received his AB from Princeton University in 1999, and he further received a PhD from Harvard University in 2003. He held an NSF Postdoctoral Fellowship at UC Berkeley before starting as an assistant professor at UC Santa Cruz in 2006. From 2013 to 2016, Dr. Weissman went on leave from UCSC to join the faculty at Yale-NUS College in Singapore. He is currently a professor of mathematics at UCS. His research focuses on number theory and representation theory, the network of conjectures and theorems known as Langlands program. His recent work integrates covering groups such as the metaplectic group into the Langlands program. Collaboration on this work is supported by the Simmons Foundation. His book is titled An Illustrated Theory of Numbers, and it conveys scholarship in mathematics and its history in new visual manner. Connections between visualization and number theory can also be found in his 2019 work on the arithmetic of the arithmetic conjecture groups. Thank you. I can now give the platform to Dr. Weissman.
Okay, well, thank you very much. Today I'm going to talk about prime numbers and some kind of history of them and some interesting ways to experiment with them. And the goal is sort of maybe to tell you some things about prime numbers that you might not learn in school when you might learn about them in primary school even, but sort of why are we interested in them and how do we study them? It's been going on for a long time. And maybe bring some visual kind of data analysis techniques into it. I don't really know the audience's mathematical background, but a lot of the talk will be using not much more than a bit of algebra. I might put a little integral symbol in once, but it shouldn't really be necessary for most of the material. I'm not so used to this format over Zoom. I'll try to keep my chat window open. So if you have questions, you can throw them into chat and I'll try to keep an eye, or maybe one of our organizers can to speak up if I miss a question in chat, but I'm happy to take questions. I've prepared maybe 30, 40 minutes of slides, which I'll lecture off of. Slides can go by quickly. It's good that it's recorded so that you can go back if you want, but you can ask questions in the midst of the slides and there'll be time at the end, I guess, for questions too. So to get things going, I'm going to try to share a screen. Let's see if I can get this to work. Okay, you've given me permission, so that works. Can everybody see this? Maybe I can get a little nod or a thumbs up or something. Does this work? Okay, that's great. So I'll tell you about prime numbers, this kind of set of numbers that I enjoy working with so much. And the talk has a couple of theses to it. So one is historical. Humans have thought about prime numbers for over 2,000 years. The first real mention of prime numbers that I know about is in Euclid. So that was about 300 BC, so 2,321 years ago or so. Another is a bit of an unusual take. I say unusual like most mathematicians might not say the same sentence, which is that prime numbers are the most interesting data set in mathematics. So I'm trained as what they call a pure mathematician, which means that I'm not really trained in data analysis, though these days I do some. But I think that prime numbers form an interesting data set. We look at genetic data sets and astronomical data sets, but prime numbers themselves form an interesting data set. And the last little point, since this is kind of, I don't know much about CYW really, but I get the impression that it's very much kind of getting involved in research, sort of at the border between sort of science fairs for youth and research science at the graduate level. This is sort of somewhere in between in a way. So prime numbers are kind of nice because you can start experimenting pretty quickly with just a little bit of programming knowledge in a computer, you can actually do some interesting things. So let me tell you a little bit about the history. Again, let's see if I can pull up a chat window just in case. Always disappears on me. Okay, so I'll start with a little history from Euclid to Riemann. And this is Euclid's Elements. So Euclid, you might have heard of in the context of geometry. He wrote the Elements or compiled them or something. We think around 300 BC, so 100 years after Plato or so. Ancient Greek mathematician living in Alexandria, modern day Egypt. This copy of the Elements, like a lot of ancient sources, we don't actually have an original or anything. The earliest complete edition is from 888 Common Era, so a good 1,000 years after Euclid. This is it. So this is this manuscript, and the Clay Mathematics Institute, they actually funded the full digitization of this, so you can actually see it at a very high resolution. This is somewhere in book 7 of Euclid's Elements. It's open to that page. And if you zoom in really close, somewhere down where my mouse cursor is, if that's visible, you'll see these two words in Greek. And these two words say protos arithmos, which sounds a bit like English if you say it quickly or something. Arithmos is the word number. It's the Greek word for number. And protos means the first. And this is Euclid's term for prime numbers. They're the protos arithmos. The first numbers are the prime numbers. It's kind of odd that he uses the word first. I mean, they're not, I would think of like 1, 2, 3, 4 as the first numbers, not maybe the prime numbers like 2, 3, 5, 7. But Euclid is kind of meaning first in the sense of like, first in the almost creationist sense, like there was one, the unity, and then after one came the prime numbers. Those were created next. It has kind of a mystical meaning almost. And so this edition of Euclid, this is in Greek, this manuscript, but it sort of traveled around and was translated into many different languages. So here's another edition. This is a manuscript from the 13th century. It's an Arabic translation by Al-Tusi. This is from book 9 of Euclid's Elements. And this is where Euclid proves something really amazing, which is that there are infinitely many prime numbers. So if I start listing the prime numbers, they start with 2, and then 3, 5, and 7, and then 11, and 13, and 17, and 19, and I can kind of keep going. Euclid proves that they'll keep going forever. You can never stop. Well, you can go on forever without running out of prime numbers. It's not like they end anywhere in particular. And this is the part of the manuscript in the Arabic translation where Euclid proves this fact. So there's another mathematician I want to bring up next. So Euclid proved the infinitude of primes, that there are infinitely many, around 300 BC. And then Eratosthenes did something kind of neat, which is he kind of brought data analysis into it in an ancient sort of way. He gave us a way to actually produce really big lists of prime numbers. So I sort of wonder if anybody has heard of Eratosthenes. He's more famous for something else in a different science. If you want, you can put it in chat or something. I wonder if anybody's heard this name. See, I'll give you a. Nobody wants to take a risk at the chat? Of course, you can Google it. Yeah. So he calculated the circumference of the Earth. Yeah, so he's famous for doing this experiment where he basically at the points in the day where the sun was highest in the sky, he looked at the shadows in 2 locations, one in, I think, Aswan, modern day Aswan in Egypt, and another maybe in Alexandria, I can't remember, a bit north. And in one location, there was no shadow. The sun was directly overhead. It was the longest day of the year. And in the other location, there was a shadow. And by measuring the difference, he kind of knew how far apart these towns were. He was able to kind of calculate the circumference of the Earth and did a pretty decent job in this approximation back around 250 BC. So Eratosthenes is most famous for that. So Dr. Domingos Ramirez asks, how are equations written? They're not really written as equations. It's all geometric. And there aren't really variables per se. There's these diagrams, and so there's discussion of like the length of a line segment being a unit or a prime number for a length, but no equations really, no equal signs. Okay, so Euclid, then there's Eratosthenes, and I'll explain what Eratosthenes did. We know about Eratosthenes, again, not through Eratosthenes, but a couple hundred years later, there's a mathematician named Nicomachus who actually just says, this is what Eratosthenes did. Maybe I'm a little careful about this history stuff, but my wife is a historian. And so I always have to be careful, you know, and she's kind of made me appreciate like the difference between popular history. So there's a lot of books about history of math and other things. Popular history would say, Euclid proved this. But a historian would say, okay, what's the, how do we know that? How do we know whether Euclid wrote something or not? Or why do we attribute it to Euclid? There's kind of a long manuscript history that's sort of just as interesting. So okay, let me tell you what Eratosthenes did. This is his method for making lists of prime numbers. And I'll show you how you can use this method to find all the prime numbers up to 100. Well, 0 and 1 aren't prime, and the first prime is 2. And so what you do is you take 2 and you circle it like this, and then you kind of cross out all the multiples of 2, all the even numbers. So those are kind of crossed out with these red stripes here. And the next number that's not crossed out is 3 right here. So 3 is prime. It hasn't been kind of crossed out by a smaller number. So you circle it, and then you cross off all the multiples of 3. Just like this. So I've crossed out 3 and 15 and 27 and 6 and 9. They form this nice pattern of diagonal stripes. Because all those numbers that I've crossed out, those aren't prime. 6 can't be prime, and 9 can't be prime. 12 can't be prime because they all have 3 as a factor. And the next number that's not crossed out is 5. So 5 must be prime. And you cross out all the multiples of 5. 5, 10, 15, 20, 25, because those can't be prime. And those form some nice vertical stripes in this picture. And then you do the same thing for 7. And 7, the stripes kind of go this way. 7, 14, 21, 28, 35, 42. All those numbers get crossed off. Now here's the kind of miraculous thing about this, is that I've done this for 4 numbers, 2, 3, 5, and 7. And if you look at any number in this grid that's not crossed out, like I look at 47 here, or 53, or 73, or 89, 71 is not crossed off. Any number that's not crossed off is prime. So by doing 4 of these crossing out processes, I've managed to find all the primes up to 100. So we say that in 4 sieving steps, each step is called a sieving step. A sieve, as I understand, is like it's like a filter, you know, like you want to drain your pasta, you kind of put it into a sieve, or if you want to like find some gold and filter out the dirt, you use a sieve. So in 4 of these sieving steps, just crossing out multiples of these 4 numbers, you can find all the primes up to 100 pretty quickly this way. You don't actually have to test each number. You don't say, hey, is 89 prime? Look for factors or anything. You can actually just do this crossing off and do it. Here it is. I wonder if we've got any programmers here. I know I sort of enjoyed programming when I was in high school. So I was in high school in the 1990s, and so I learned how to program in Pascal back then. And I just kind of had fun playing with it. This is Python code. So nowadays I program in Python. And this is the full Python code for the sieve of Eratosthenes. It's not the most efficient possible, but it'll run pretty well. And you can Google search, you can Google Python sieve of Eratosthenes, it's hard to spell, to find better code for this. And this will produce a list of all the primes up to a given number n. So if you want to find all the primes up to 1,000,000, it takes 168 steps, and it runs in milliseconds. You know, maybe 1/100 of a second or less. It's really, really fast. So today we can produce lists of primes instantly on our computer with, what is this, about 10 lines of computer code. Kind of a cool thing. And I've kind of set this up here. If you might or might not be able to read this code too quickly, the first thing that you do is you kind of say that 0 is not prime and 1 is prime, and 2 and the rest of the numbers, you set them to be true for a minute because they could be prime. And then you kind of run through the numbers, and if a number is prime, you kind of create this stripe. And then you cross off all the numbers in that stripe. That's the basic outline. It really is what I displayed in the last slide. So this is how you do it today. But the sieve of Eratosthenes was used in the 1700s and 1800s as well. And they had the tables of primes up to a couple million by 1800. There are actually some kind of cute gadgets that they used to make these. So instead of crossing out stripes, they made little stencils where you could sort of put the stencil on your paper, then fill in the little missing things. There were rollers they had with little marks, so they could just sort of roll over a sheet of paper and paint a whole bunch of stripes at once. And using these techniques, Gauss had tables of primes up to a couple million. Oh, okay, so in R, there's also a prime, so I didn't know that. Cool. Thank you. So Gauss had these tables, and as sort of a hobby, he'd count how many primes were in intervals. Like how many primes were there up to 1,000? How many primes were there between 1,000 and 2,000? Between 2,000 and 3,000. So every night, according to a diary that he wrote, he'd just kind of count the number of primes in a new interval. And he made these tables. This is one that he sent to a former student of his. And you know, even if you don't read German, you might be able to recognize unter means under. And this is the number of primes that are underneath 500,000. So the way that I read this is that there are 41,556 prime numbers up to 500,000. And there are 78,501 primes up to 1,000,000. So this was Gauss's working by hand. Right around 1800, he started doing this. And he noticed something kind of unusual, which is that the primes kind of gradually spread apart. You know, they're really common at first, like 2, 3, 5, 7. That's like 4 out of the first 10 numbers. They get a little less common and a little less common, but not too quickly. And empirically, and this is what I'm talking about experimental techniques, what he found was that if he chose kind of a random number, n, then the chance it was prime was about 1 over the logarithm of n. And this is the natural logarithm if you've seen logarithms. So this describes kind of the frequency of primes. It's not like a number has a 50-50 chance of being prime or like a 25% chance of being prime. But depending how large the number n is, the chance is about 1 over the logarithm of n. This is what he found by looking at these tables. And he used this to give an estimate for the number of primes up to a given number. So how many primes are there up to 1,000,000? You can use some probability theory to estimate this based on his 1 over log n formula. And his estimate was this number 78,627. And this was his kind of estimate. And the actual number was 78,501, at least he thought. And then he looked at this error, which was about 126, which isn't a bad, you know, it isn't off by too much. Sorry. So this is what Gauss did. We're not talking about finding a formula for all the prime numbers or something like that. It's a way to like estimate how many prime numbers there are in a given range. So this is maybe a good time for a little aside. So approximation is kind of a strange thing when you study math, because a lot of people think about math as like an exact science, like we get exact formulas for things. But approximation is sort of its own field of math involving statistics and things as well, and probability theory. And approximation it really is something precise if you can kind of control the error in your approximation. So if you know that x is approximately equal to y, and the error isn't too big, you can make that a precise statement, and that's kind of a mathematical thing. So there are two ways of thinking about approximation and how good it is. One I call the absolute error. So if you have kind of a correct number and an approximation, your error is just the difference, maybe the absolute value of the difference. So if your guess is a is 1,000,000 and the actual number is 1,010,000, you're off by 10. That's an error. There's another useful notion which is called the relative error. The relative error is the size of your absolute error, but divided by the correct number. So if your number is really 1,000,000 and you're off by 10, that's a very small error, kind of relatively speaking, percentage-wise. The absolute error is 10, but the relative error would be like 10 out of 1,000,000, 0.0001 or something. More zeros than that, I guess. So I just want to say something about what Gauss did and what sort of errors there are in it. And then I'll get to some more experimental things. So after Gauss, about 100 years later, two people, Hadamard and de la Vallée-Poussin, proved the prime number theorem. Actually, it's a little, this name, I don't know, are there any French speakers here who could say what de la Vallée-Poussin means? And I know my French pronunciation is terrible, but oui. Okay, so I wonder if Dr. Dominguez Ramirez, do you know what this word means? Funny thing.
Does it have something to do with Poisson, the mathematician?
No, it's not that. It's actually it's an animal.
Ah.
Yeah, it means roughly of the chicken valley.
Ah. All right.
I think. So I forget his first name, but he became the baron of the royalty almost, the baron of the chicken valley. And once he got this title, official title, then that's apparently becomes his kind of how you refer to him. And so now we're stuck referring to this poor person as of the chicken valley, which I think is kind of funny. Okay, so that's also a mathematician. And Hadamard, also French, they worked just about at the same time and proved the theorem just about in the same year in 1896. And what they proved is, maybe it's best to put it this way. They proved that Gauss's approximation for the number of primes is very good. In fact, the relative error approaches 0 as the number gets bigger. So Gauss gave us a way to count the primes up to 1,000,000 or up to 1,000,000,000 or up to 1,000,000,000,000, however big you want. He gives a nice estimate. And what Hadamard and the Chicken Valley guy, they proved that the relative error goes to 0. In other words, that is an excellent approximation. It becomes better and better as the number x gets larger and larger. Like if you go up to 1,000,000, your relative error will be very, very small, 0.001% or something like that. Okay, so this is what they proved. They proved that kind of Gauss was onto something, that he was right in this method of approximation. This is something that I think that everybody who talks about prime numbers has to talk about, which is the Riemann hypothesis. So the prime number theorem, which was proven back in 1896, tells us about the relative error in Gauss's approximation. And the Riemann hypothesis is a conjecture about the absolute error. Like, what's the absolute difference between the number of primes up to x and this Gauss's approximation, this integral thing, Li of x. And it's brought up a lot because it's a very famous problem in number theory. It's been around for over 100 years. And for the last 20 years or so, there's been a prize associated to it. So if you prove the Riemann hypothesis, if you can really get at the absolute error in Gauss's approximation, then you get $1 million. Not that I suggest everybody go and work on this right now, but if you're motivated by wealth or something, then you can always try to work on $1 million problem. And there's some strict rules for what's accepted. So don't write something that's 3 pages and send it to me and then ask me for $1 million. I'm not the Clay Mathematics Institute. You have to publish the paper and have it accepted and things. Okay, so this is still, it's there's $1 million prize for something that was basically conjectured or studied first about 200 years ago about the prime numbers. So more precisely, the million-dollar conjecture is that the absolute error in Gauss's approximation is bounded by some constant times the square root of x times the log of x. I don't want to focus on this too much. There's a little formula here, but so if you want to estimate the number of primes up to 1,000,000 using Gauss's formula, this says that your error will be about 1,000. That's the square root of 1,000,000. The logarithm term doesn't really give too much, maybe a couple thousand, but that's the right order. All right. So this tells you in a way, it explains why in Gauss's table, these numbers on the left column here, these are the count, how many prime numbers are there up to 3,000,000. This is Gauss's approximation, and this is the error. And the error is so much smaller than the numbers you're working with. The Rayman hypothesis is the explanation for why and how much smaller these numbers are. That's what we're trying to understand. But let me get on to some things that are easier in a way. And then I think that anybody can experiment with who has a computer and learns how to program a little bit. So I want to talk to you about different populations of primes. So one way of looking at populations of primes is you can call some of them red and some of them blue. And the way that I'll do this is that forgetting about the prime number 2, which is even, all the other prime numbers are either one more than a multiple of 4, like 5 and 13 and 17 and 101. These are all one more than a multiple of 4. Or they're blue, which means that they're one less than a multiple of 4, like 3 and 11 and 23 and 599. These are all one less than a multiple of 4. And you can ask, like, are there more red primes and blue primes? Or the other way around? Are they equally likely to occur? There are infinitely many primes. Are there infinitely many red primes? Are they mostly blue, for example? So you can run this on the computer very quickly. If you look at primes up to 1,000,000, there's this number of them. Gauss actually, Gauss was counting by hand. He was off by 3 or something. And among all these 78,000 primes, about 39,000 are red and 39,000 are blue. So it seems like it's just about 50-50. And here's a little graph. So the blue line is the proportion of primes that are blue, and the red line is the proportion of primes that are red here. And maybe I'll give you a minute to look at it. I wonder if you see anything, or like can think of a research question, or what might be interesting about this. Maybe you can type it in chat if you like. Yeah, there's a symmetry. The symmetry is a little bit artificial because every prime is either red or blue. So I'm actually kind of double graphing something, saying, if it's 52% blue, then 48% red. Yeah, convergence, I'd say, is something that seems to be happening. Like these lines seem to be going together to be approaching 50-50 over time, getting closer and closer to 50-50. Anything else? There's one more thing. Yeah, there's kind of some jumpiness to this. Yeah, so the lines converge, it seems, to the 50-50 point. Fractal-like structure, I kind of agree that it has like a fractal-like structure like a random walk does. If you look at different scales, it has bumpiness at all scales. There's one kind of basic thing. Well, maybe I'll go to the next slide or two and we'll see it. Well, but first I can tell you that de la Vallée-Poussin, he actually proved that in the limit you get a 50-50 ratio. That red and blue primes, if you make this graph extend, then in the limit they get to 50-50. In other words, the quotient is 1. They're equally likely to occur in the limit. But Chebyshev, again, like counting these things in the 1850s, way before computers, noticed that the blue primes look at this blue graph. It's not like these things are crossing each other all the time. The blue ones seem to be in the lead almost all the time. This is something that Chebyshev noticed. In fact, these graphs do cross, though you can't really see it at these purple vertical lines. These are places where that blue line really quickly dips below the red. It's just too small to see at this scale. So in fact, they do cross, but most people believe that the blue line is above the red line more than 99% of the time. This is something that people try to prove. Like, it's a subtle thing. Like, a lot of people would just care about the limit being 50-50, but if you care about which line is above most of the time, the blue primes seem to be winning the race almost the entire time. Okay, so there are more experiments. I wonder if you were going to try something like this, I wonder if anybody has a question you try to ask next. It's kind of an exercise in, like, imagine you're a mathematician, like, what's the next thing you might investigate? Any ideas or aspiring mathematicians? It's one of the toughest questions, I think, in science, is like, no ideas. You know, a lot of times when we're in school, I think, you know, the teacher sort of asks you a question and you're supposed to answer it. You know, it's that sort of process. And whereas in math or science, I think one of the toughest things is actually like formulating your own questions. And so it's a good thing to practice, I think, in like math and science classes, like, you know, be curious. And it's like, okay, you see a situation, like, make yourself stop for a second and wonder. It's like, huh, I wonder what's going on here. I wonder what else I might look into, variations on something. Because I don't know, at some point, it's like a scientist, nobody's going to give you the questions anymore, right? You have to kind of think of them on your own. There's some easy variants of this that you can do. So for example, instead of 4n plus 1 and 4n minus 1, you can look at things that are 1 more than a multiple of 3 and 1 less than a multiple of 3 and do the same thing. Or you can look at the last digit of a prime. The last digits of primes tend to be 1, 3, 7, or 9. Are those equally likely? There's lots of these style questions that they exhibit similar phenomena to this that are worth investigating. And people are discovering new things. Even a couple of years ago, there was a new discovery about, if you look at the last digit of a prime and the last digit of the very next prime, there's some strange correlations there that are very unexpected. Okay, so let me finish. I want to just show you one thing. This is a little bit more technical, and it's more kind of breaking research. This is research over the last, well, 50 years and things that were solved in the last 10 years. So this is about this class of equations called elliptic curves. And the simplest example that I'll use is this equation right here, y squared equals x cubed plus x plus 1. And you might not have seen the graph of this before. Like in school, you might see graphs like x squared plus y squared equals 1 describes a unit circle. If you graph this equation, like you go into, I went to Desmos to graph this. If you don't know Desmos, it's a great graphing calculator. It's free to use. So you can graph equations like this. There's nothing too special about this one. I'm just choosing it as a good example. When you graph it, it looks like this curve here. It's called an elliptic curve, though that's like a weird historical thing. It's not ellipse. And what I want to do with the equation is something weird. I'm going to do something called counting its mod p points. And bear with me for 5 minutes or so while I explain what this means. So I'll start with counting what are called the mod 3 solutions to this equation. And the way that you do this when you work mod 3 is that you just consider the numbers 0, 1, and 2 for x and y. And I plug them into this formula. Oops, sorry. So I plug 0 in for x and 1 in for x and 2 in for x. And I plug 0 in for y and 1 for y and 2 for y. And I evaluate this formula here for x and y. And this is the table that I get. So when x is 0 and y is 2, I get 3. So be it. And so when x is 1 and y is 0, I get -3. So I make that table, and then everything is kind of being considered mod 3. So what I look at next is I look at which numbers in this table are multiples of 3, and I highlight them. Those are these kind of pink circles here. 3, 0, and -3 are multiples of 3. And then I count the number of pink circles. And there are 3 of them. So that's the process. So you start with your equation, you put all the variables on one side, you plug in 0, 1, and 2, and you count how often the result is a multiple of 3. Those are the steps for it. I'll do it one more time for 7, just to kind of make it clear. So now when I do things mod 7, they say, what I do is I plug in the numbers from 0 through 6 into this formula right here. I make this big table, and then I look for multiples of 7, like 14 is a multiple of 7. And so to find the multiples of 7, what I'll do is I'll divide by 7 and take the remainders. And these are all the remainders. And the remainder 0 is where I've got a multiple of 7. There's a 0, there's a 0, there's a 0, there's a 0. Right there. And so there are 4 numbers in this table that are multiples of 7. And I count the dots, and I get 4 of them. So that's the process that takes 5 minutes or so. And here's something that the German mathematician, I think Hasse was German, proved in 1933, that if you count these pink dots, then NP is the number of pink dots. NP ends up being very close to P, and the error is bounded by twice the square root of P. This is what Hasse proved. So it says that if you want to count the pink dots, it's approximately P. So P was 3 in the first case and P was 7 in the second case. And the error is bounded by twice the square root of P. So the correct minus the estimate is less than or equal to 2 root P. So this is all good. It's a useful bound, and these things are actually useful in cryptography, and it's important for applications. But later on, people started asking the question, well, this is all nice. You know, you've got the correct answer and the estimate, and you've got a bound. But is that the best bound? I mean, does the correct minus the estimate, is it closer to 0 on average, or is it closer to the worst case on average? So this is the next step of difficulty, which is that you know that the error is bounded by twice the square root of P. And then they define, this is something that was done by Sato in the 1960s. If you look at NP minus P and divide by the square root of P, it's bounded by 2. And anything that's bounded by 2 is twice the cosine of some angle. So they associate this, and this is kind of a weird idea. They define an angle alpha P to be basically like the arc cosine of the quotient or something like that. So I'll put this in chat. So alpha P is equal to the inverse cosine, which is called the arc cosine of NP minus P all over 2 square root of P or something. And they looked at how these angles were distributed. Basically, when the angle is when the angle is 0, that means that your error is kind of your approximation is as bad as possible. And when your angle is 90 degrees, your error is 0. So depending where this angle is kind of a measure of how good or bad the estimate is. And in the 1960s, Sato computed a whole bunch of these angles. So he took a whole bunch of equations and a whole lot of prime numbers, and he made some histograms of these angles. And he found this shape showing up. This is his journal from the 1963. And you might be able to see here, I don't know how it looks on your screen, but there's a little thing here that says sine squared of theta graph. And what this shows is that when you look at these errors, the errors tend to be kind of closer to zero. This is zero in the middle than at the ends. It's not like the error is sort of spread out as much as it could be. It's concentrated in the middle there. This is a version that I made on my computer. Again, it took maybe half an hour of programming and less than a second for it actually computed to find this graph, which is a version of what Sato did 50 years ago. And this shape, this is what Sato found. He found that the shape, time and time again, it appeared to be just like the graph of y equals the sine squared of theta, where theta goes from 0 to 180 degrees. This was Sato's discovery. Again, kind of an experimental discovery using some very early computers, actually. Okay, so this was turned into a conjecture that was known as the Sato-Tate conjecture, and this is one of the things that interested me most when I was starting to study mathematics. So I was an undergraduate in the 90s and a graduate student in the 2000s, and this conjecture was something that everybody was talking about. It's like, maybe we could prove this, maybe we could prove this, and I didn't prove it. Many other people did, and around 2008 and 2011, this was finally proved that if you look at enough primes, then the shape of this graph actually resembles closer and closer to the shape of the sine squared of theta graph. So very subtle kind of statistical properties of primes. You take primes, you count these dots, you get these numbers, you make some angles, you make this histogram, and you see these kind of perfect shapes pop out. So this is sort of what I call high level like research math, modern mathematics about prime numbers, these kind of things. So just to kind of like finish today, a couple of things. Maybe you're here because you're interested in math or science or something. So my field of math it's number theory. So I study things about prime numbers and integer equations and things. And one thing I really love about it is that very often the questions themselves are pretty simple to state. You can write them down and sometimes you can explain them even to like 10-year-olds or 12-year-olds or something. But actually answering the questions requires like really deep and interesting things in geometry and algebra and calculus, and all these different techniques come into play. And the other thing about this is that there's this idea that there's like pure math and people who prove theorems, and there's applied math, like people who do math for physics or biology or something. But a lot of like pure math like this has kind of experimental computational aspects. And that's something that I really enjoy too. And I like programming. Like I program almost every day a little bit. I really love programming Python and playing with things. And so it's kind of cool that now anybody who can program, even just like a single course in programming, can really like make progress on some research by experimenting with things and by learning to ask the right questions. And a lot of people always ask like, why do you actually care about prime numbers? And for me, I just think that they're mysterious and beautiful. Like I've been looking at them for a while, so I just really love thinking about them. But some people really like, and it's like the people that like the $1 million prizes. They're like, okay, but what's this good for? Why is this useful? And I might just mention that big prime numbers are used all the time in internet security. So for cryptography purposes. So every time if you have a Gmail account and you check your email or something, or probably true for Outlook too, there's some giant prime numbers behind the scenes. You're not seeing it, but there's some prime numbers on the order of like 300, 400 digit primes that are being used in the cryptographic algorithms to keep your data secure. And this is true for everybody. This isn't just fancy stuff. Now this is day-to-day, every time you check something on the internet. There are some big prime numbers floating around there in the background. So people really do want to understand prime numbers better to sort of improve this, improve data security a lot. So, all right, I've been talking for a while, like 45 minutes at least. So thanks for Om. He's been my contact through this whole process, and the other CYW organizers. And I'll hang around for a little bit for questions. So thanks. I'm happy if you speak up or in chat.
All right. Thank you very much, Dr. Weissman. I think everyone on this Zoom call and also people who are watching from the YouTube live stream can definitely agree that this was a very insightful presentation, as we have learned how humans have been thinking about prime numbers. And I've also realized how prime numbers are actually an interesting data set in mathematics. And is when you concluded how prime numbers are actually useful and how they are actually being used. Thank you very much for that. So I think if anyone has a question, you are free to unmute your mic and ask the question, or if you are more comfortable in using the chat, you can just type your question in the chat and Dr. Weissman will be able to answer you. Thank you.
Yeah, I have a question. Firstly, congratulations for your job. I'd like to know what's your motivation and the inspiration to study math and a such hard subject like this.
Yeah. So what's my inspiration? I guess I've been interested in math and science since I was a kid. And I think when I was younger, I was also interested in physics a lot, and I studied some physics in college. And I was a strange kid, I really liked reading math books when I was, 10 and 12 and 14. I mean, it's sort of before the internet, to age myself a little bit, but you used to go to the bookstore and Dover publishes these really cheap books. So, you spend like $1 or $2 and you get this old book and it's like all very mysterious and I couldn't get very far, but I'd try. So I picked up math books and just try to learn things on my own. I'd say it started to get hard for me when maybe I studied geometry and then calculus. Like I thought I was just really good at it. And then I hit some classes where it was very difficult for me. And that was a bit of a shock at first, but then I sort of realized that like everything gets difficult that's interesting. After encountering, I think, the difficulty for a while, I sort of began to really enjoy that part too. And nowadays, when you do research, you're working on problems that really nobody knows how to solve. And nobody knows whether they're solvable. So sometimes I'll get stuck for like 3 months or 6 months on the problem. And, but it's kind of a privilege just to be able to do that and to enjoy the process. So it's very different than teaching math, where if you get stuck on a homework problem for an hour, you get really frustrated. And now, there's actually a problem I've been kind of stuck on for like 3 years. I don't know if I'll ever get anywhere on it. I think I'm really stuck. But then, you talk to other people and they have ideas, and I love that process. Long-term problem solving. I don't think math ends up being harder than other things, except at the very beginning. I think everything ends up being hard. I've actually been working closely with some biologists lately, and I find their work extremely difficult. So I don't think one's really harder than another.
Thank you very much for that. I've received 2 questions from our chat. So the first question is, how would the Rayman hypothesis revolutionize our understanding of the number theory?
So on the practical side, I don't think it would change much. I don't think that proving the Riemann hypothesis would change cryptography, because pretty much everybody just assumes that it's true. We just don't know why it's true. And I think it's one of the most important conjectures because I give this talk about prime numbers, but there are other things that behave like prime numbers that are easier to work with. There's what's called function field primes, and there are all sorts of other prime-like things out there. And in these other prime-like things, we can often prove the Riemann hypothesis. We understand why it's true in other situations, but not in the most crucial basic one. So whoever solves the Riemann hypothesis will have to understand numbers in a way that nobody does right now. And nobody quite knows what that's going to look like. I mean, I think it'll be done. I don't know if Riemann hypothesis will be proven in my lifetime or not. But someday somebody will understand numbers well enough to do it. And I think that that by itself will be revolutionary. If you can do Riemann hypothesis, then the understanding that you'll have will be good enough to prove lots and lots of other things as well, I think.
Right. Thank you very much, Professor. And the other question is, one of the big problems in number theory is the Collats conjecture, and some say that it is unsolvable. So what is your opinion on that?
So if you don't know it, it's a fun thing to play with. It's a little game where, just for those who haven't heard of it before, you start with typically like a positive integer, like 3 or something. And then if it's odd, you triple it and add 1. So 3 gets tripled to 9 and you add 1 to 10. And if you see an even number, you cut it in half. So 10 gets cut in half to 5. And that's odd. So you triple it and add 1 to 16. Then you have it to get 8, have it to get 4, have it to get 2, have it to get 1. 1 is odd, so you triple and add 1 to get 4. That's even, so you get half it to get 2, have it to get 1. Then you're stuck in a loop, 1, 4, 2, 1, 4, 2, 1, 4, 2, 1, over and over and over again. So that's what I call the Collats process, or the 3n plus 1 process. And the Collats conjecture says that no matter what positive number you start with, you end up stuck in that same 4, 2, 1 cycle eventually, if you run enough steps. Okay. I don't have an opinion on whether it's solvable, but it seems out of reach. Like, it's one of these like borderline cases where if you watch how these numbers dance up and down, it's like they end up all going down to 1, but it's a close call. If you change the rules a little bit, like you change 3n plus 1 to 5n plus 1 or something, things kind of blow up and they go off to infinity and all sorts of other things. And if the numbers get small, it becomes too easy to prove. This is like right in that middle zone. And there are a few results that go in different directions. So might prove that if you want to solve an entire class of problems like that, then you won't be able to. Basically, there's some unprovable things that are reminiscent of Collats, or that include Collats and other things in it. So it doesn't show that Collats itself is kind of unsolvable, but it shows that you're on the verge of, you kind of have to discuss issues of provability when you discuss Collats conjecture. So from what I know about it, it's kind of at that edge where we're not sure what's provable or not. On the other hand, Terry Tao proved some probabilistic results kind of asymptotically. It looks like if you choose a random number in a suitable sense, you've got a probability 1 that'll actually get caught in a cycle. So it's kind of like you can prove something is 99% true and 99.9% true and 99.99% true, but you can't prove that it's all the way true. And so he thought deeply about it and kind of couldn't quite get there either. So I think there are some obstructions. I just don't know. I haven't worked on it myself enough to sort of know exactly why we can't solve it, but a lot of people spend a lot of time working, a lot of really, really strong mathematicians, and they haven't gotten there yet. So I don't know. It's fun to work on.
Thank you. I think also has a question.
Mm-hmm. Yeah.
Yes, so this might be a little bit naive, but I just wanted to ask, like all these, like we have a lot of unproven conjectures at this point of time, like we are talking about. And like besides the Collats conjecture, we have the ABC conjecture and the twin prime conjecture and stuff like that. So like as a physicist, we like to think that things are related fundamentally. So like, do you think that there will be eventually some kind of fundamental connection between all these currently unproven conjectures on the prime numbers?
I think some of them are more connected than others, but I sort of understand the physicist's instinct towards like a grand unified theory. But in a way, maybe that's because there's one universe that you study.
Yeah.
Whereas mathematicians, they study a lot of different things, and they study games that play by different rules. So I don't see like a reason for like a grand unifying thing. Now some things, like if you take the ABC conjecture, since you mentioned it, and you take the Riemann hypothesis, and you take the Birch-Swinnerton-Dyer conjecture, which is another $1 million problem. Those three problems. All three of those problems have basically been solved in an analogous setting, this what's called a function field setting. So there's a different system of numbers in which all three of those problems have been solved. So you might say, once we really understand how to adapt methods from that realm of numbers to the numbers we love, the whole numbers, the integers, once somebody manages to figure out how to do that the right way, maybe all three of those conjectures will fall. Maybe we'll get them all. So that's why I think any one of them would be incredible, because and lead to other things.
Yes, thank you so much for that. And I also wanted to ask you, a quite different question. So like, I wanted to ask you, what field of mathematics would you have liked to pursue research in, if not number theory?
Yes, it's sort of a funny question. Like, okay, let me tell you another little secret, which is that I don't think number theory is really a field of mathematics in a way. It's kind of a source of problems more than a set of techniques. So number theorists care about whole numbers and prime numbers and all these things, but that's what we want to study. But maybe in the same way as like an astronomer might want to study like what they see up in the sky. But the actual techniques that people use are different. So there are analytic number theorists who are using analysis, basically calculus of various kinds, to study number theory questions. And there are arithmetic geometers who are using geometry to study number theory questions. Personally, my specialty is in representation theory, which kind of mixes some algebra and geometry. And that's what I use to study number theory problems. And I really love that set of techniques. So I'd probably do something with representation theory or geometry. Like I really love geometry. So I like things where I can visualize stuff and draw pictures and have used geometry just, even if not directly seeing it, but just kind of like my mind's eye a little bit to get intuition.
That's great. That's great. And like you mentioned representation theory. So like, is group theory used a lot?
All the time.
Number theory research?
All the time. Yep. Yeah. So this is one way that I can talk to physicists. So, for example, if I talk to Stefano, he's that way up the hill in the physics department. So he does kind of particle physics, dark matter stuff, and so he'll send me a note because he's using some group and representation theory in his work, and I'll send him some things back, and we can talk about representation theory a lot. It's very applicable in quantum field theory, where particles really are representations in the mathematical sense, and also in number theory, it's now kind of a central technique in studying number theory.
Yeah, that's so good to hear. Thank you so much for all your answers.
Yeah, of course. So anything else? I can hang around for another 5 minutes if there's anything else, or maybe I don't know if you have another talk going on. I don't want to.
Yeah. So if there are any last questions, you can just unmute your mic and ask or send a chat. Right now, there's a question. So the person says that you have published a number of articles and also you've published a book. What's your motivation? What keeps you moving, researching and working in the field of science, in particular, working in the number theory?
I mean, it's hard to say. I mean, it's the job, I think. This is. I never really thought about not doing it in a way. You can say like, okay, why do I actually go into work every morning? Get my paycheck and things, all that. I look at, being a professor means that my job is, roughly half teaching and half research. But maybe it's like 40-40 and 20% answering emails and being on committees and things. So part of my job is teaching students, which I love to do, and then part of it is doing research, which is sometimes a pad of paper or on the computer. And writing papers is the way of, getting your research to that final stage, to kind of finishing it. So it's something that I enjoy enough that I think I do it, I'm fortunate to be a tenured professor, which means that I have a lot of flexibility, and I could stop doing research, but Maybe part of what got me to this place is that I enjoy doing it enough that I do it anyways. So I really just love working on these problems, and I'm lucky to have a job that actually supports me to do it.
All right, thank you very much, Professor Weissman. Is there still any other question from the audience? I don't think so. So thank you very much, Professor. Thank you very much for your time. I think we have learned a lot today, and also you have inspired people to consider the field of mathematics. So with this, I think all the participants and the audience who have attended this lecture, and you have a good day.